Eye-shaped keyboard for dual-hand text entry in virtual reality. There are many applications for text entry in VR, such as entering account passwords, chatting through typing, and taking text notes. However, there are still many problems with current VR text entry methods, despite the large amount of research in the field of VR entry. Most current technologies still use a common QWERTY layout with dense keys, which causes high error rate. In addition, physical QWERTY keyboards are not easy to carry around and virtual QWERTY keyboards are slow to trigger. Other text entry techniques, such as gesture-based or head motion-based text entry techniques, are either expensive to learn, have low input speeds, are task-loaded, or cannot make full use of the cooperation of both hands. So we have designed an eye-shaped keyboard for text entry in VR, which is novel, fun, efficient and quick to get started. Compared to previous text entry keyboards, our keyboard retains the key sequence of the QWERTY keyboard, making it easy for the user to learn, while providing high trigger speed and two-handed coordination. Similar to the shape of dual eyes, the keyboard layout is divided into two parts, the left eye and the right eye. One eye has two eyelids, each of which is curved and has 7 to 8 keys. When using the eye-shaped keyboard to enter a letter, the user needs to move the ray to the inner eye region and then move the ray from the inner eye region to the corresponding key region. At the moment the ray enters the region, a character is typed out. The autocomplete is applied on eye-shaped keyboard. It infers words based on the entered characters and lists the 4 most likely words. These 4 words can be selected respectively by moving the left and right joysticks to the left and right. We have designed a pilot study to optimize the parameter configuration of our eye-shaped keyboard. First, we rearranged the eye-shaped keyboard in 3 kinds of layout. In the 3 layouts, the spacing between upper and lower eyelids decreases successively, namely large, medium and small. Experiments have shown that medium spacing layout performs better significantly. Then, we deployed 2 extra feedback technologies on the keyboard, color scale marking for keys and recoloring of the rays when triggerable. However, experiments have shown that neither of them improved users' typing efficiency significantly. Therefore, we conclude that the input feedback of the original keyboard is relatively intact. In this study, we conducted an experiment to evaluate the eye-shaped keyboard. In user study 1, participants were required to type with eye-shaped keyboard, virtual QWERTY keyboard and circular keyboard, all of which are controlled by handle ray. Post-hoc test shows that compared with other methods, with eye-shaped keyboard, error rate and user's average handle translation speed are significantly lower. Concretely, eye-shaped keyboard performed significantly more efficiently than circular keyboard and kept a comparable efficiency compared with QWERTY keyboard for beginners. In user study 2, we recruited participants to test the potential of the eye-shaped keyboard by continuously typing on the keyboard for 40 minutes per day. This part of study lasted 3 days. The results showed that users' performance could be substantially improved by continuous training. Typing speed reached an average of 19.9 WPM and a maximum of 24.9 WPM in the last section of study, and is still on trending upwards. We have designed the eye-shaped keyboard. It is fun and efficient, and performs significantly more efficiently than circular layout with lower task load and more accurately than QWERTY layout for beginners. It is also potential for trained users. With the increase of training, typing speed will rise.